In this presentation, we will go through shear resistance in columns. Much of the presentation is going to focus on cyclically loaded columns, but some of the concepts will be applicable as well to just statically loaded columns. By the end of this presentation, you should be able to identify the maximum shear that a column can experience based on moment capacity, explain how shear is resisted in columns, construct a moment axial load interaction diagram that includes shear effects, design a column to resist cyclic loading, summarize the important design principles for columns, and identify dangerous column types. The maximum demand on a column with lateral load will be at the top and the bottom of the column. If the column's pushed to its maximum capacity, hinging is going to occur at both the top and the bottom of the column. The maximum possible shear in the column from lateral loads can be found to be related to the maximum moments by summing the moments about the top and the bottom. So here our maximum shear is equal to 2 times our moment capacity divided by the length of the column. So essentially the fundamental point here is that the maximum shear on the column depends on its maximum moment capacity. Similar to what we previously studied in this class, shear in columns is going to be resisted by both concrete and steel. Our VC component comes from the tensile strength of the concrete before cracking, and then our different after cracking components that we talked about before. Just like before, only the steel that crosses a shear crack is going to resist the shear, and we can find the shear resistance using our same equation that we used before, shown here. Like before, columns will resist shear differently based on whether they're cracked or uncracked. Prior to cracking, the shear is resisted by only the concrete. And we can find the shear resistance using the equations shown in this table here from ACI 318. So whether we have minimum shear reinforcement or we don't have minimum shear reinforcement. And while before we didn't include an axial load in these equations, now when we're talking about columns, we will have an axial load. So this N sub U is going to be positive for compression and negative for tension. Note that VC shall not be taken less than 0. So if you have tension in the column, it's going to decrease the shear contribution VC, but VC can not be less than 0. Shown on this slide are the similar limits on some of the equations. So we have an upper limit for VC, which needs to be less than 5 square root F prime C BWD. And we also have an upper limit on the amount that that axial compression can benefit our shear strength. So that's limited by this equation here. We also have the same size effect modification factor, that lambda S, which we can calculate using this equation. Note that we only need to include the size effect modification factor when minimum shear reinforcement is not provided. So otherwise, size effect doesn't impact the shear strength. After cracking, the shear resistance is made up of aggregate interlock, the shear strength of the uncracked concrete in the compression block, the residual tensile strength in the concrete, V sub CR here, the shear reinforcement crossing the crack, V sub S, and the dowel action provided by the primary longitudinal reinforcement. As long as you have minimum shear reinforcement provided, we can assume that our after cracking shear contribution from these 4 different components, so not including the shear reinforcement, is greater than the original VC that we found in the before cracking state. So we'll just use the VC equation that we saw in a couple slides before to calculate our VC after cracking as well. Unlike our beams, though, column shear is often cyclic. Cyclic shear can break down the aggregate interlock and reduce the ability of concrete to resist shear. So while the surface begins rough, or the surface of a crack begins rough, and you have that aggregate interlock component, as you cycle shear along that interface, it's going to smooth out the interface, and until eventually you have a smooth interface with no more friction capacity. So during cyclic loading, this VC is going to progress to 0. To design a resilient column to resist cyclic shear, you should either design the column so that the concrete resistance exceeds the applied shear, and what this will do is keep the column uncracked, which ensures that there's no breakdown of the aggregate interlock with cyclic loading. Or you can provide enough steel so that your steel component or your steel shear resistance exceeds the applied shear. And what this does is it ensures that as the shear is cycled and your VC approaches 0, the column still has sufficient shear strength to resist the applied shear. So doing one of these will ensure that you have a resilient column to resist cyclic shear. We can integrate the concrete and steel shear strength contributions into our moment axial force interaction diagrams. And we can do this by using some of the equations that we had from the beginning of this presentation. So the first thing that we'll do is we'll take the equation that we had from the beginning, and we'll define an M sub C as the moment is governed by VC. And then we can change that equation, so we'll have a moment M sub C equal to V sub C times L divided by 2. We can then substitute in our V sub C equation from ACI into our M sub C equation, and we'll get this expression here. So you can see this equation relates our moment in terms of our axial force. So we can use this equation in our moment axial force interaction diagram. This equation from ACI 318.19 and on is simpler than the previous version in ACI 318.14 because VC is no longer a function of M sub U. So in the previous code, ACI 318.14, we needed to come down to a quadratic to be able to relate our moment to our axial force. In the example problem that we'll cover on the next couple slides, we will integrate the concrete shear resistance into our moment axial force interaction diagram for this section shown here, with a 20-inch depth, a 12-inch width, and 3 number 9 bars on both faces. We're given the data shown, and 2 values that we'll need to calculate are our rho W, which is just 3 times 1 square inch, which is the area of our number 9 bar, divided by 12 inches, our BW, times D, which is 17.5. So here we'll get a rho W of 0.0142. We also have our gross area, which is just the base times the height, so 12 times 20 is 240 square inches. Next, we can find the M sub C for different applied axial loads. So we'll start with finding M sub C for N sub C equal to 300 kips. We can plug in our 300 kips compression, so it's positive, into our NU over 6AG expression to get a stress here of 0.21 KSI. We can compare this then to the upper limit of 0.05 F prime C, which is 0.2. And here, since the 0.21 is greater than 0.2, we need to go ahead and use the 0.2 in our VC equation. So then in VC, we plug in our different values. So 2 times 1, we're using normal weight concrete, so we have a lambda factor here of 1.0. times the square root of 4,000 PSI. In ACI, we remember that we have to use PSI under any square roots, and then I'm dividing by 1,000 pounds per kip to get our units into KSI. And then we add in our 0.2 KSI and take this times 12 inches are BW times D 17.5 to give us 68.6 kips. We need to compare this value to our upper limit of 5 square root of 66.6 kips, and we can see that our 68.6 is greater than the 66.6, so we need to use the upper limit value of 66.6. So this is the VC that we'll use moving forward. We can plug this V sub C into our M sub C expression. So MC equals VC L over 2. So we plug in our VC, our L, divide by 2, and get an MC of 3,996 kip inches at this point. So this is the moment associated with an axial load of 300 kips compression. We can then go ahead and repeat this for enough axial loads to complete our plot. And here is our moment axial force interaction diagram. The black line is our original plot. The blue line is including a slenderness effects, where we have a slenderness ratio KL over R equal to 40. And the red line here is now our moment governed by our V sub C. So as long as we are inside these curves, so if we have a point right here, we know that our column would not fail because of slenderness effects or because of shear failure. We can then do a similar exercise with our steel shear resistance, taking our V sub S equation and plugging it into a similar M sub S equation here. So we can see our M sub S is our moment controlled by the steel shear resistance, and we can plug in our VS and get this equation here, which we can then integrate into our moment axial force interaction diagram. From our previous example, if we have an S equal to 8 inches with 2 number 4 bars as our transverse reinforcement, we can calculate our VS. So 2 number 4 bars have an area of 0.4 square inches times the yield strength 60 KSI times D 17.5, and then divided by 8 inches gives us a VS of 52.5 kips. We can then plug this 52.5 into our moment expression. So the VS times our length, 120 divided by 2, gives us an M sub S, a moment controlled by the shear or the steel shear strength contribution of 3,150 kip inches. We can then add this moment governed by our V sub S plot to our moment axial force interaction diagram. So you can see the red line here is our moment governed by our V sub S component, and you can see the green dotted line is the one that we looked at previously, our moment governed by our V sub C component. So any point inside this red line means that V sub S will not control the failure of this column. The concrete and steel shear strengths can be combined to include a complete shear resistance, V sub N, into our moment axial force interaction diagram. So here you can see this is the moment governed by V sub N. So we can use these diagrams to adjust our stirrup spacing and our specimen size and our concrete strength to ensure that we don't have different types of shear failure. So if we just have a static shear, then we have a V sub N outside of our moment axial force interaction diagram. We know that when we apply a lateral load, we're going to have hinging at the ends of the columns before shear controls. So we can also have our V sub C, where if we keep all of our points inside this green dotted line, then we know V sub C will not control failure. Or V sub S, if we keep all of our points inside this blue dotted line, then V sub S won't control failure. So we can use this diagram to help design our column and prevent a shear failure under static or cyclic loading. Here's a summary of what we've gone through so far. So we see the state of damage and we see VC and VS in this table. When we're at an uncracked state, we have a VC equal to the VC that we can calculate using ACI 318. Our VS, our steel, it's not effective. It does not engage until cracking occurs. After we have incline cracking, our VC is going to be above the value that we calculate in using ACI 318, and our VS is going to be engaged. So we can find our VS using the expression here from ACI. And the actual concrete resistance is due primarily to the shear friction across the compression block. So during reverse cyclic loading, our VC is going to progress to 0. As the shear cracks cycles and reverses, our shear strength or our concrete shear resistance is going to break down, and our VS is going to pick up what the VC is dropping off. So the VS will initially start at the value we can calculate under static shear, but this too is going to degrade below as the flexural cracks kind of open up. The shear reinforcement will become less effective. So ultimate failure is going to occur by sliding shear across these cracks. With these things in mind, some good design principles are we want to design our column to be below balance. We want to design our column such that our VC plus VS are outside of our MN diagram for flexure, and when there's no chance of load reversals, and that way we can ensure shear doesn't control. If we do expect load reversals and cyclic shear, then we want to design either our VC or VS to be outside of our moment axial load interaction diagram for flexure. And this will make sure that the column either doesn't crack in shear or it has enough shear reinforcement to resist the shear demand entirely by itself. And the last design principle to kind of highlight is that as columns become shorter, they're more likely to fail in shear. So you can see our shear is inversely proportional to our column length. So a shorter column means a higher shear demand. This slide has some more in-depth explanations of the generalizations that we talked about on the last slide. So if you want to pause and read through these, you can pause the video now. The observations on the previous slides can be simplified into 3 essential design parameters. Number 1, the axial load, the applied axial load compared to the axial load capacity of a column. The transverse reinforcement ratio, which is a measure or which controls the ductility of the section and how much confinement benefits we have and if the longitudinal reinforcement will buckle or not. And then also the shear span ratio, which is a measure of the length of the column compared to the depth of the section. So we're going to look at on the next couple slides how we can design using these 3 parameters to come up with a column that's resilient and can resist cyclic loading. Our first design parameter is our axial load. We can remember back from our column discussion that we're going to have the best performance if we have an axial load less than our balance point. So typical balance points are going to be about 1/3 of the pure axial capacity. And the pure axial capacity we can approximate as F prime C times the gross area. So we can use this to estimate our column size based on our axial demand and make sure that we are less than our balance point here. So for good axial behavior, we want to work kind of below 1/3 of the pure axial capacity. From our previous discussions on columns, we know that for our transverse reinforcement ratio greater than about 0.01 is going to give us a good curvature ductility and confinement. And we also need to provide the spacing less than about 4 times the diameter of our longitudinal bars to make sure that we don't have buckling of our longitudinal bars. typically providing number 4 bars at 4 inches on center is going to be a good starting point to give us a good ductile column. Next, we can derive some principles based on our shear span ratio. So since the maximum shear that can be applied to a column depends on its moment capacity and length, a shorter column is going to have more problems with shear than a longer one. So here you can see the same columns with a length of 120 inches versus 240 inches. You can see with 240, our shear curve is almost outside of our moment axial force interaction diagram, but when we're at 120, our shear capacity is cut in half. So you can see the green curve is now kind of inside that moment axial force interaction diagram. So the shorter the column gets, the more shear critical it is. The first step in coming up with an acceptable shear span to depth ratio or length to height ratio for the column is coming up with typical ranges for our V sub C. So you can see V sub C is a more complicated equation than what I'm showing here, but for typical N values or axial load values, we're going to be between 3 and 5 times the square root of F prime C BWD. So we can use this simplification in the following slides to come up with an acceptable range for our, or an acceptable upper bound for our length to height ratio. We can then derive an expression relating the amount of longitudinal steel and the shear span to depth ratio to the required concrete resistance. So this derivation is based on an approximate equation for M max or M balanced, an approximate equation for the shear resistance, and our shear span to depth ratio being equal to M divided by V times D. So I'm not going to include the derivation, but we can get this equation for our K, and for a typical value of F prime C of 6 KSI and phi here of 0.7, we'll get a K equal to this equation here. So we're going to plot this equation on the next slide, as we'll see, versus our A over D ratio. So shown on this slide is the equation on the last slide plotted with different reinforcement ratios. So here's the curve for 0.1, 0.2, and 0.3. We can remember that we'll typically be in the 3 to 5 range for our K, or will be between our shear resistance will be between 3 times the square root of F prime C BWD and 5 times the square root of F prime C BWD. So we'll be right in this range. And note how you read this plot here is if you're on the left side here, so this point here at 5 times square root of F prime C BWD for a rho G of 0.01. If we had an A over D less than that, we're unsafe, and if we had an A over D greater than that, then we're safe. So we can see here for this point, for a rho of 0.01 and a shear strength of 5 times the square root of F prime C BWD, we want an A over D greater than 2.3. This slide shows how we can relate our shear span to depth ratio, or A over D, to an L over H, or a length to column size ratio. So our shear span in a typical column with a lateral load is going to be A equals at L over 2, so half the column height. So then our A over D ratio is going to be L over 2D. And our typical D is going to be around 0.88 times H, 0.88, 0.9 times H. So we can set this equal to 2.3, which is what we found on the previous slide in the plots that we developed. And we'll see that this gives us an L over H ratio of about 4. So for typical good design, we want an L over H ratio for our column to be greater than between 3.5 and 4. And that'll give us good behavior and make sure shear doesn't control. So on this slide is a summary of our good design principles that we've been going through on the last couple slides. In this table, you can see the axial load over here on the left side and the aspect ratio on the top of the table. And you can see we're broken up into different cells based on what aspect ratio and what axial load we have. So if we have an axial load less than balance and we have an aspect ratio greater than 3.5 to 4, we will have good flexural behavior and good energy dissipation. So this is where we want to shoot for, or this is what we want to shoot for when we're designing a column to resist seismic loads. If we have a shorter column, but still less than balance, we'll get inclined cracks forming slowly. The column will slowly degrade in shear, but it'll depend on the longitudinal steel we have. So we will have limited ductility, but we will still have some ductility if we're designing below balance. When we go above balance, if we have a larger aspect ratio, so greater than 3.5 to 4, we're going to have flexural behavior, but it will have limited ductility. If we have a column above balance and with an aspect ratio less than 3.5 to 4, our column's going to fail rapidly in shear, and we will have negligible ductility. So we want to avoid this cell here, and we want to shoot for a column with an aspect ratio greater than 3.5 to 4 and an axial load less than balance. And we also want to make sure that we provide sufficient transverse reinforcement. So have a rho S greater than 0.01 and a spacing less than or equal to 4 times dB. On the next couple slides, we're going to go through some dangerous columns, some columns to avoid when we're designing. So on this slide, we have two types of columns with very small aspect ratios, or small L over H ratios that can happen. The first is when we have a partial infill wall. So as a designer, you may be designing a column to go from the bottom here up to the next story. So you can see it's a column with a larger aspect ratio, but the architect may come in and want to add some kind of partial infill wall. If the partial infill wall is stiff enough and comes right up to the column, then this partial infill wall is going to make the column think that it's much shorter. So this column would think that its length was only from the top of the partial infill wall to the next story here. So you can see that is a short column, and that would be shear critical. Another type of column that can control is when we have a change in column height in a story. So here we have a longer column on the left side where the elevation's lower. And then when the elevation increases, if you wanted to keep the next story height the same without having to excavate all this material, maybe you just shorten your column. So this column has a smaller L over H ratio. It's going to attract more force because it's stiffer, and this will be a shear critical column. So these are two columns that you want to try to avoid when designing in seismic regions. Shown on this slide is a column that's shear critical because of a partial infill wall. So you can see our column goes from the middle of this top story to the ground, but we have a partial infill wall right here that is stiffening the column. So this column actually thinks that it's only goes from the top of the partial infill wall to the bottom of the next partial infill wall. So this creates a column with a very small aspect ratio, L over H ratio, which makes it shear critical. So there are two different ways that you can avoid these shear critical columns because of partial infill walls. You either need to create enough separation between the infill wall and the column so that the column can oscillate and move and not be affected by the wall. Or you could just take the wall the whole way up and make this a shear wall rather than a moment frame. So just try to avoid leaving these short shear critical columns that are caused by these partial infill walls. There are two additional examples of partial infill walls creating shear critical columns on this slide. So you can see here a partial infill wall only on one side of the column, still made this section shear critical, so a short column behavior in there. And then over here on the exterior, we have, again, a kind of partial infill wall, a railing on the outside of this parking garage that was cast in place, and we have a shear critical column right here. Here's another example of a partial infill wall. So you can see we have a very stiff wall right here on the left side, and we have kind of less stiff walls here and right here next to the opening. So you can see that this wall provided a lot of stiffness to the column, but these walls broke down. So when these walls broke down, we had a short column here that became shear critical and controlled failure of that column. Another type of dangerous column is a soft story column. So typically architects want big open lobbies without many walls, and often they'll have longer heights, or the columns will have longer heights than the rest of the building. So this creates a soft story at the bottom with a stiff upper structure. So during a seismic event, the top of the structures just kind of oscillate back and forth, and these columns on the soft story are going to break down. So you can see here's an example of a soft story. A softer lower portion of the building with a very stiff top portion of the building. The top portion will cause the bottom portion of the structure to break down. Here is another example of a soft story column. So a stiff upper structure and a softer lower story with just a few columns, and it's not sufficient to resist the lateral loads here. And here's another example of a soft story columns. So we have a soft lobby level and stiff upper section of the building, and we can see the breakdown of the columns here. So essentially, to prevent this, you just need to make sure that you have a similar stiffness between the different stories, so that you don't have all the movement and the breakdown of the columns on the lower story. So make sure you have a stiff, just stiffness compatibility between stories. Shown on this slide are some additional references that go through the shear strength of reinforced concrete columns. And that concludes this presentation.